Methods for evaluating DC arc flash incident energy in BESS. My name is Terry McKinch, and I'm the Electrical Safety Manager for Nexamp Energy. Albert Marquand from ETAP, and I will be doing this presentation. Background for today's presentation. Albert and I did this at the 2023 IEEE IAS Electrical Safety Workshop, ESW, in Reno, Nevada, USA. I'm going to talk about energy storage battery types and battery energy storage installation types. Types of energy storage batteries. Aspects to be considered when determining the battery short circuit current density. Types of energy storage batteries: lithium ion, lead acid, nickel based cadmium, or nickel based, and flow. Lithium ion. Lithium magnesium oxide. Advantage: it's fast charging. Disadvantage: only recently entered the CNI market. Lithium, nickel, manganese, cobalt oxide. Advantage: high specific energy. Again, only recently entered the CNI market. Lithium, nickel, aluminum oxide. Advantage: high specific energy and more stability, but it's relatively new. Lithium iron phosphate, long cycle life, does not require ventilation or cooling, but it has a risk of thermal runaway. These batteries have high energy density and low self-discharge. They do not need prolonged priming when new. One charge is sufficient. They are low maintenance and periodic discharge is not necessary. Most of them are still comparatively expensive to manufacture and are subject to aging. They require protection circuit to maintain voltage and current within its limits. Lead acid. Advantage: it's really reliable. Requires watering though, and transportation restriction. Does need ventilation because of the hydrogen gas. Valve regulated lead acid, VRLA. Advantages: the valves regulate off-gassing, requires little or no maintenance, can be installed in hard-to-reach applications, but it is sensitive to temperature. Lead-acid batteries are inexpensive, with prices range between $382 and $399. Have the lowest self-discharge rate among the rechargeable batteries, have high specific power, low specific energy, and are capable of high discharge currents. Not environmentally friendly, are heavy, are relatively inefficient as for their charge and discharge compared to other batteries. Nickel base, nickel cadmium, long cycle life, do not require ventilation or cooling. Disadvantage: low specific energy, risk of thermal runaway, toxicity of the calcium or cadmium. Nickel-based batteries have been used in large-scale energy storage projects as they perform well in all types of temperatures. Nickel cadmium is the most common nickel-based battery technology used. They are often preferred for off-grid installation as they provide a reliable backup system and don't require high maintenance. Vanadium for flow batteries: vanadium, iron chromide, and zinc bromide. Advantages: modular and scalable, low flammability, low cost, and low environmental impact. No need for complex heating or cooling. Overcharging or discharging does not damage the electrolytes and the electrodes. Disadvantage: relatively low efficiency as compared to lithium ion. High cost for repair and maintenance. Flow batteries are comparatively new to the battery storage market. In recent times, they're becoming a strong competitor to lithium ion in the energy storage domain. They are rechargeable, in which the electrolyte flows through one or more electrochemical cells from one or more tanks. In these batteries, one can easily increase the energy storage capacity by increasing the quantity of the electrolyte stored in the tanks. The choice of redox pairs is often used as a description of the slide, type of flow battery. Battery energy storage installations. Type of installation affects the choice of calculation methods and hazard level. Best installation types, grid scale installations, containers may contain DC only or both AC and DC. Grid scale BESS can be in remote locations with high sunlight exposure, such as desert areas. Personal protective equipment should effectively protect the personnel, but should not cause heat exhaustion or obstruct the movement. Thermal runaway is a factor, but since AR clothing is FR, then protection should be efficient. This is one of my projects in California. It's in the middle of a desert. It's quite a ways from just about anything, but it's a grid scale installation. Each 2 or 4 of these was a circuit. I think I had 16 circuits for a 650 megawatt PV site. These are a couple of my batteries types. The one on the left is what you just seen, those containers, and the one on the right are a different one. Best installation types more. The one on the left is the AC and best container open low voltage AC enclosure. Best container open DC battery combiners on the right. Best PPE considerations. PPE introduces other hazards such as heat exhaustion or accidental contact with energized conductors. VLA battery rooms are required to include an eye wash station in the event of chemical exposure. Some battery types exhibit thermal runaway and need to have cooling systems to mitigate the risk. Electrocution is a risk, and rubber insulated gloves or blankets must be used in the approach distance. This is a typical eye wash station. I think it's in one of my substation control room in the battery room. And now I'm going to turn it over to Albert.
Thank you for your presentation, Terry. I chose to work with Terry McKinch because he has worked around large grid-scale BESS installations for a while, and he has a tremendous wealth of field experience. I certainly felt blessed and enjoyed spending time at his facilities, looking at all the BESS installations in our publication. He also provides a lot more details about what he talked about earlier, about BESS hazards other than thermal incident energy. He also describes the PPE requirements to protect yourself against chemical exposures and also helps to raise awareness about the venting and potential thermal runaway hazards. All of this information can be found in the publication that he mentioned during his presentation. Before we go into details, let's understand the challenges that engineers face when calculating DC arc flash incident energy. As we move through our presentation, we will see slowly how ETAP provides solutions to each of these challenges. The biggest challenge is the lack of accurate methods. For many years, engineers only had the maximum power method, which could yield overly conservative results and even under conservative results. The other big challenge that we have is that the battery short circuit current is highly variant, and we need better methods to account for the battery resistance, inductance, and operating voltage variations, such as the state of charge. And also, the last big challenge is how to deal with the various conductor arrangements that we saw are present in equipment, as Terry explained very well during his presentation. As I said before, I partnered with Terry to be able to create a refined DC arc flash model for BESS based on various BESS conductors, arrangements, and configurations that we saw at his installations. This effort led to a great research work, which we also validated using laboratory test results, which were publicly available to us. So before I talk about the ETAP DC arc flash model for battery energy storage systems, validation and all this other effort that went behind it, I like to fill us in and spend some time on how the battery is modeled under short circuit conditions. Battery short circuit current, as I said before, is highly dependent on the cell arrangement and the arrangement of the connectors for each cell. Batteries are typically arranged in cell rows for substations battery packages, for example. The line cables that we see here have their own inductance and resistance. The cell connectors have their own resistance and inductance, which sometimes can be modeled as a loop wire inductance. And in fact, this is the method that Terry and I chose to use to calculate their inductance. This arrangement is used because it's easy to visualize. We also have modeled the battery cells as bus bars when calculating their overall inductance. Determining the battery cell inductance can be difficult. For our paper, we chose to model them as bus bars. However, as you saw during Terry's presentation, they can be arranged in multiple shorter rows and taller stacks in the racks, right? So there are multiple arrangements that we can find, and as we saw during Terry's presentation, they come in different sizes and arrangements. Due to time constraints, we could not add more cell row arrangements for our calculation examples, but you should consult your manufacturer to get details on how to determine the cell inductance and enter it into your ETAP model. The battery equivalent circuit for short circuit calculations is shown in this figure, where RB represents the internal battery resistance, EB is the internal voltage of the battery, RC is the resistance of the cell connectors that we saw previously. The term LCC represents the inductance of the cell circuit. LBC is the inductance of the battery cells that are considered as bus bars, as I mentioned in the previous slide. The internal inductance of a single cell can be neglected as it is typically set to 0 in most models. At the far right-hand side of the end circuit, we have RL and LL, which represent the line resistance and inductance. Conductors, which are the conductors leading to the point of the fault, perhaps somewhere in the system downstream. The equivalent circuit that is of a short circuit, if a DC internal voltage through an equivalent resistance and inductance is used. In this case, we notice that we have some basic first order differential equations to solve as published in IEC 61660. These equations can be used to determine the time variancy of the current of the battery. This slide shows the battery current during its evolution, where Rk is the quasi-steady state, or what we call in ANSI as the steady state short circuit current, and is typically determined in IEC for a 1 second duration. Of course, we do not use a 1 second duration as a norm or default to calculate the incident energy. That depends on the practice and the standard that you follow. The plot also shows the time to peak and rise and decay time constants. The point in time marked as TK can be considered or used as the fault duration. This will be the time used to determine the incident energy as we integrate the current as a function of time. Well, at this time, we can ask ourselves the question on how can we use all of these equations and plots to represent the various battery types that Terry talked about, the various chemistries. Well, as was described in the paper and during Terry's presentation, the various battery types such as lead acid and lithium ion can be represented using the same equations, but the various time constants, quasi-steady state currents, and peak values vary based on the current density and the battery type, and those can be entered into the library or are readily available as part of the ETAP library. Batteries with higher current density will have slow decay times and high steady state values. Lower current density batteries will have higher rise times and short circuit decay times. In the paper, we also talked about lithium ion and the differences between that and lead acid, for example. The simulation model that ETAP uses is based on the Stokes and Oppenlander equations from the Ammerman, P.K. Sen, and Tammy Gammon paper, which at its time was an award-winning paper. What ETAP does is to make each of the parameters from this set of equations have a variation versus time. The lab tests that I evaluated in the past, several laboratory tests, were used to develop methods and to adjust the gap in other parameters as a function of time. This slide simply shows how the current, voltage, and resistance change and are dependent on time. Once again, here we see the two nonlinear equations that I mentioned before and that are used to solve for the arc resistance and voltage. What is important to note here is that each parameter now has a time dependency. I would like to stress this point. This is what allows us to capture the effect of the conductor or the electrode configurations that we saw are available in the equipment during Terry's presentation. Let's explore now to see how we can interpret some of these conductor orientations or electrode configurations that we saw from Terry's presentation. The series butted configuration could be inferred to be present in the battery cell connectors. The vertical bus bars were predominant in several of the equipment images that we saw during Terry's presentation. In the test result literature that we consulted to do this work, we had also observed vertical parameters, vertical parallel, and series butted electrode configuration tests with various gaps. So therefore, we utilized these results to validate our model. We also saw during Terry's presentation that some of the equipment had electrode configurations with barriers to the top, to the sides, and these barriers could constrain the DC arc column movement or expansion. This, of course, changes the arc characteristic behavior, which in turn changes the delivery of the incident energy. This image shows very clearly one of the physical phenomena for DC arcs, which is called the arc elongation effect, which can be present in some of these electrode configurations. This test was done during a different research collaboration project that I had with Bill Sekulik and Peter McNutt from the National Renewable Energy Labs, or NREL. However, this effect in batteries may not be nearly as important for the calculations instead of the one that we will see next. Conductor erosion. So what is it? What are we dealing with here? Conductor erosion essentially represents the amount of material that is burnt away, or the burn back in the conductor as a function of time. Essentially, as this material burns away, and depending on the electrode configuration, that gap between conductors can increase, and therefore it could become more resistive. Higher resistance could deliver more arc power and higher heat flux energy from the arc. The problem is that if we don't capture this phenomena, we could calculate lower incident energy values that then could be released for particular configurations. Here, we see the before and after images of a series or butted conductor DC arc flash laboratory test that was performed in some of the literature that we consulted to develop the model. The DC bolted fault current available at the source was about 20,000 amps, and the conductor rod diameter used here is about 25.4 millimeters. The burn back, as you can see here, reached several inches. In this chart, we can see the arc current and the arc voltage measurements from the test from the previous slide. We can notice that the current reduces from its initial point to its final point by almost 50%. The arc duration was approximately 2 seconds. The initial and final arc voltage difference is substantial here. The cause of this decay in short-circuit current is mainly due to the increasing arc resistance as the gap between conductor increases. Unfortunately, there's a consequence to this behavior or this phenomena, which has not been captured by other thermal incident energy models available or even other standards such as IEEE 1584 for AC. The ETAP model predicts that the heat flux or incident energy is not linearly proportional to time, but in fact may change depending on the life of the arc and how it expands or it moves or how it consumes the material in the conductors. Here we can see a result of the comparative analysis that we used to validate this. The first row represents the actual laboratory test results, which came in at 42.5 calories per centimeter square. The second row represents the results using the ETAP simulation model, but without considering the effect of the conductor erosion. The value came in at 22.5. The third row simply represents the ETAP model simulation results with erosion, and which came in at 43.5 calories per centimeter square. And last, of course, as I mentioned, one of the biggest challenges of this whole thing is the overly conservative results, which could be used or derived by using methods such as the maximum power method. This slide simply summarizes the test configuration that we use for another set of laboratory tests, which we further use to validate the model. Here we can see, again, in orange color, the ETAP model test results. In the blue color, the results of the actual test results. We see great correlation. And again, as I mentioned before, the maximum power methods are very high and irrelevant. One of the last sources of comparative analysis that we mentioned in our paper and that we use for comparisons of the DC Arc Flash model for BESS is a full comparison against a full EMT time domain simulation. As Terry mentioned during his presentation, the various types of battery chemistries used have significant difference in short-circuit current behavior. In this test, we have a simulation of a lithium-ion battery pack, which was faulted, and the DC arc current was plotted as a function of time. As we can see, the rise time constant of a lithium-ion battery is very short when compared to that of other battery types such as lead acid. This comparison is just another example of the amount of model validation and the quality that you can expect from ETAP software. The ETAP method results seem to yield more consistent results since, as you can see on the right-hand side, the arc current remained below the short-circuit currents throughout the duration of the arc, as should be expected. So what are our key takeaways? Well, as we saw, ETAP's transient DC Arc Flash solution for BESS or battery energy storage systems using the IEC 61660 standard definitely helps us to estimate a far more accurate incident energy value. That's a tremendous solution to one of the biggest problems in the industry. Also, we know that transient arc current simulations provide far more accurate determination of the arc duration, which we will do once we do more research on the effect of these transient currents on overcurrent protected devices. We also learned that neglecting conductor erosion effects may lead to underestimation of the incident energy. And last, I would like to leave you with the concept of a second part of research that will take place, where we will focus on the effect of the transient DC arc currents on current limiting fuses and other overcurrent protecting devices. More work is needed in order for ETAP to develop new technology that is not available in any of these standards. With that, I would like to say thank you for the opportunity. Thank you for attending ETAP Spark, and please drop any questions in the chat. Thank you.